Hi, my name is Jonathan Scott, professional land surveyor, professional engineer. We're going to take a look at the surveyor licensing exam equations today. We're going to do a review of those and I'll give you some examples. And basically I'm going to go right through the reference handbook that you're going to be given for the exam. I'll go through the equations and explain them and give you examples for each of them. Okay, the first equations that come up in the reference book are the following. You have straight line equations, quadratic equations, and some trigonometry. Okay, we're going to focus in on these first ones here, on the straight line equations. Okay, we'll start out with an example with the very first equation, the general form of the equation. So the general form is this ax plus by plus c equals 0. For example, let's go ahead and say you have 2x plus 3y minus 6 equals 0. You're going to put that into slope-intercept form, basically solve for y. You can see the standard form of the equation up here solves for y. And then y equals minus 2/3 times x plus 2. So in this equation with the standard form, you have that m, which is the slope. So the slope is minus 2/3 in this case, and then b is 2. So the y-intercept is 2. Okay, we'll take another example here. Let's say we have y equals 4x minus 7. So in this case, the m value is 4, so the slope's 4. The y-intercept is minus 7. And let's go ahead and say set x to 3. So you put it in the equation, and then you get y is equal to 5. So a point on that line is 3, 5. Okay, the next equation that we have is this, the point slope form is this right here. So it's y minus y1 equals to m times x1 minus x1. So for example, we had a slope of m equals 2 at the point 3, 4. You just go ahead and put in the values, so y1 is 4, x1 is 3, and solve and simplify for y. So that equation for that line that goes through that point and has that slope is y equals 2x minus 2. Okay, the very next formula that comes up here is a slope from 2 points. This one down here. So let's just go ahead and do an example. Just wrote out the equation here. So example, you have let's say 2 points, 1, 2 and 5, 10. You just go ahead and put them in the equation for the y and the x's, and you get slope equals 2 for this one. Pretty straightforward. And let's see, the next one's the equation of a line from 2 points. So let's say you have the same 2 points, 1, 2 and 5, 10. You're given a slope this time, m equals 2. So you're just going to go ahead and put it in that formula. So you're going to have y minus 2 equals 2x, x minus 1. So we were using this formula right here. And so the equation comes out to y equals 2x. The next equation is this angle between two lines. It's this formula here. So example, let's say line 1 has a slope of 1, line 2 has a slope of 2. You just put the terms in the equation and you get the angle. So the angle between the two lines is about 18.4 degrees. And that's just the same thing wrote up here. Okay, the next equation that comes up here is this: two lines are perpendicular if the first slope is equal to minus 1 over the second slope. So went ahead and made an example. Here's the equation. Example, if one line has a slope of 3, perpendicular slope would be minus 1 over 3. So like for example, if you have two equations like this here, that term here, the 3 and the minus 1 over 3. These lines are perpendicular. Okay, moving right along, the next equation is this distance between 2 points right here. So, for example, went ahead and wrote out the equation here for you. And so I'll go ahead and do an example at 2 points, 2, 1, and 6, 4. You just go ahead and put the y's and the x's in the formula. Voila, there you have a distance is 5 between those 2 points. Pretty straightforward stuff. So here's a survey style example. Let's say we have these 2 points, A and B. Calculate the slope, and then calculate the distance between them. So then you can go ahead and get an equation through that line, equation through that one of the points there. And that covers all these equations here. Okay, we'll move on to the next equations in the book here. Back to the reference book. And the next ones are these quadratic equation, and you get into some trigonometry. So for the quadratic equation, it's this formula here. You're basically solving for x in this equation using this roots formula. So for example, like say you have a rectangular lot, has an area of 600 square feet, and let's say the length is 10 more feet than its width. Find the dimensions. So you take the two sides, you're going to multiply them, so you have x times x plus 10, and that's going to be set equal to 600. Go ahead and write this out into this form so that follows the quadratic formula form. So then you can use that equation to set the numbers based on A is 1, B is the 10 that in this form, and then the C is this last 600. So you put all that in there and you get x equal to, you get two answers, 20 feet and minus 30. So you're going to reject one of them because you can't have a negative length. So the length is just going to be 20 plus the width of 10, so you have 30, so the answer is 30 feet, so the answer is the dimensions would be 20 feet by 30 feet. And the trigonometry, it's basically your basic sine, tangent, and secant and all that. I'll just do an example for one of these. A surveyor stands 80 feet from the base of a utility pole. So he's standing right here. It's 80 feet away from this pole. The angle of elevation to the slope is 35 degrees, so this angle here is 35 degrees, and you're trying to find this height right here, this h. So set up your tangent and equation is up here, so it's kind of like the opposite over adjacent. So that would be the tangent of that 35 is going to be h, which is the opposite side of it, and the adjacent side is the 80. And solve for h, so you get h is equal to 56 feet. And the next equation that comes up is this law of sines. So for example, the way you use this in the triangle form by 3 survey points, A, you have the first angle is 42 degrees here, the second one's 68 degrees, and you have one side you're given as 120 feet. So you can set up the law of sines. A over the sine of A is equal to B over the sine of B. So you go ahead and put the terms in. 120 over the sine of 42 is equal to the B over this angle sine. And solve for B, so you get 166.3 feet. And moving along to the next set of equations in the reference book, more of the trigonometry equations. So we'll go one by one on these. First one is this law of cosines. And then, for example, let's say you have a surveyor occupies a point A and measures one side B 150 feet and one other side is 200 feet. And that A angle is 40 degrees. Find the distance A between the other 2 points, you're trying to find this side here. So you can use the law of cosines. You can take one of the formulas and just solve for A, because you're given B, C, and angle A. And you get A is equal to 128.6. And the right triangles is the Pythagorean theorem. For example, a survey crew measures 120 feet on the east and then 50 feet to the north from a corner. Find a straight line distance C. So you have this side is 120 and this side's 50. Try to find this side here, so you can set the A squared plus B squared equals C squared. You have A and B, solve for C, and it's 130 feet. Okay, the next equation that comes up, it's the inverse distance formula, which is real similar. You're just going to, for example, say you have 2 points, an easting and a northing. You can think of this as like an X and a Y basically, but easting would be 160 feet this way, 120 feet this way. So you're solving for this side of the triangle D. Set the formula, you have the N and the E, and so that D is equal to 200 using that formula right here. Okay, we're just going to move right along to the next set of equations in the reference book. And these get into the inverse direction, and you have oblique triangles. Okay, we'll start off with that first one here, this inverse direction. So like the way this thing's set up, you have quadrant 1, 2, 3, and 4, and you have an angle here in azimuth measured clockwise from the northing point here, and you're given that equation, and where the C value, depending on which quadrant you're in, you're going to add in a C number. These are straightforward problems. Like here's an example, like a surveyor computes the coordinate differences from point 1 to 2. So you have an easting of 100, so you're going over this way 100, and a northing of negative 200, so you're going down this way 200. So let's say that it puts you right around here. To think of it, and notice you're in this quadrant 2, and the angle that you're calculating is like this here. So you're going to use that formula that's given, and then once again, since you're in quadrant 2, you're going to use the C is equal to 180. You're in quadrant 2 right here, as we said. So substitute in the eastings and the northings in this equation, and use the C and calculate an angle, which is, your answer is an azimuth, so it's 153.43 degrees from here to here. Oblique triangle example. You have the law of sines and cosines here. So, for example, a surveyor measures a triangle between 3 property corners and finds you have an A angle of 38, B is 71 degrees for this angle, and you have one side is 95. Find side B. Try to find this side here. And you can set this up with the law of sines and put in the terms and solve for that B side, 146 feet. And moving along to the next set of equations in the reference book here. The next ones are area of triangle, spherical triangles, and we'll start with go by these one by one here. So for the area of the triangle, with these equations here, I'll give you an example how to use these. A surveyor measures 2 sides of a triangular parcel. So say A is 120 and B is 150. Set it up like this, and then you have one angle C, 35. You're trying to find the area of this this triangle. So you can go ahead and use that first equation since you have these known, and you put in the terms and calculate out an area of 5162.4 square feet. Next, we're going to look at the spherical triangle formulas here, if either law of sines or law of cosines, to calculate these. So for example, in a geodetic spherical triangle, a surveyor knows this B angle is a 48-degree curve. This C is a 62-degree curve, and an included angle, this angle here is 37. Find the side A, and you can use that spherical law of cosines, substitute in the values, and you calculate that angle that side makes there, which is 33.1. Okay, moving back to the reference book, we're going to look at the next set of equations here. Next equation we're going to look at is for the horizontal circular curves. And in the reference book, they define everything and they give these set equations. And let's go over these carefully here. Let's go ahead and take a look at all the different terms in this on these curves. So that the PI is the point of intersection. It's the point where the two tangents meet. The PC is the point of curvature. It's right here. It's where the curve begins. And the PT is the point of tangency. It's where the curve ends. The R is the distance. That's the distance from the center of the circle to the curve. The I, or delta, central angle or intersection angle, is the angle between the two tangents, and that's right here. The length of the curve, L, is the distance measured between the arc from the PC to the PT, so it's this distance here. And the LC stands for long chord. That's the straight distance from the PC to the PT. So that's this distance right here. The E is external distance. That's the distance from the PI to the midpoint of the curve measured outward. So it's this distance from here to here. The middle ordinate is the distance from the midpoint along the long chord to the curve. So it's that distance M right there. And then degree of curvature, this D, it's the angle that defines the sharpness of the curve. And there's also some other equations down here. You have this area of sector, area of segment, and area between the curve and the tangents. So the area of the sector is like the pie shape that forms here like that. I just kind of sketched a little bit. The area of the segment, that's for calculating this area. It's just like this top part here. And the area between the curve and the tangents, it's like that hat, kind of like the distance up here. Let's go ahead and look at an example. So let's say we're using the horizontal curve equations, compute the T, the L, and the E for a horizontal curve with a radius of 1955 feet, central angle of 29 degrees, and a PI of 9 plus 0, that's given in stations. So we can pull some equations that we need in this list here. We're going to need to calculate the T, the L, and the E. And you're given these things. So go ahead and compute out the T given that first formula. We have the intersection angle, you divided by 2 there. And then you calculate out the L using this formula here. And you calculate the E with this formula here. So very simply you have these answers for this example here. And let's look at another example. Using the horizontal curve equations, what's the degree of curvature using the arc definition for a curve with a radius of 600 feet? So the degree of curvature is this D formula here, wrote it out there, and you're given R, the radius. So you have everything you need to substitute into this equation, and you come up with 9 degrees 55 seconds. And you can convert that to the degrees, minutes, seconds format using your calculator. And later I'll give you a good YouTube video that shows you how to use your calculator, because that's a simple thing to be able to know how to do that. Switch between the two of these two things here. Okay, we're going to do another example for horizontal curves. Let's say we have a problem using the horizontal curve equations, compute the LC, M, PT for a horizontal curve with a length of 556 feet, center angle of 13 degrees, 52 minutes, and we have a PI of 15 plus 0, 0. So here's our givens, and I went ahead and put that degrees, minutes, seconds into an angular format here. First, we're going to need to solve for the radius. So I went ahead and pulled this equation here and then rearranged it to solve for r. Then you have all the terms for that. For the radius, I calculated that out. And then we're going to calculate this long chord distance here using one of the formulas here. We wrote it out for us here. So we have all the terms there. We calculate the long chord distance, and then we're going to calculate the middle ordinate m with the equation given here. I wrote it out again. We have all the terms, 16.8 feet it comes out to be. And then for the PT station, first you need to know this tangent distance, okay? So I went ahead and pulled this equation out of the list, wrote it here, tangent. You have the I and R, so you calculate out the tangent distance, 279.36 feet. Then first you're going to need to get this PC station. So the PC is going to be equal to the PI minus the tangent. So you're going to take PC equal to the PI. Once again, in stations it's 15 plus 0, 0, but the distance, just make it 1500. Subtract out that new tangent distance you got. So then now the PC is 1220.64. And then to calculate the PT, it's going to be this PC plus L distance on the curve. So your PC, once again, is the 1220.64 calculated above, plus your length, which is given, 556, and that's going to equal 1776.64. You can put that into station 17 plus 6.64. Okay, doing another horizontal curve equation example. Compute the L, the D, the T, where the I is given, and the PI is given, and you're also given the radius. So for the L, quickly you kind of look at these and figure out what you need. So you need to compute the L. There's a formula for the L. Go ahead and put it here. You need the D, so you go ahead and pull the D equation right here. You need the T, and you go ahead and pull that equation right here. And you're given these things. Go ahead and convert your intersection angle to the degrees, and given these things, go ahead and put it in for the length, calculate a length, and then the degree of curvature. You use this equation here. You have everything you need, and I calculated out 4.9 degrees, and then I converted that to degrees, minutes, seconds. And then the tangent, went ahead and used this formula right here. You have all the terms, so your answers are as follows for those. Okay, so we got this other horizontal curve example. Given a horizontal curve, radius of 2549 feet, center angle 36 degrees, PI 12 plus 0, 0. What is the PC and PT of the curve? Okay, so we know we're going to need the tangent distance and that length of the arc to get these things. So these two equations, pull them over here. Given the radius and angle of interior, so then the PI, so we're going to compute that tangent with this formula here, and so the PC right here is going to be the PI minus the tangent distance. So I take the PI, and I'm going to convert it from the stations to regular form, 1200, and then minus the tangent distance there, so you get 371.78 feet. And now compute the length of the curve with this formula up here, and you get 1601.58 feet. So the PT is going to be the PC plus the length of the arc, these two, so it's 1973, or in station form it's 19 plus 73.36. Those are your two answers. Okay, let's go back to our equation book here. Next set of equations that comes up here is going to be the vertical curve formulas. Now these are all explained. You have the length, vertical curve, you have the point of vertical curvature, which is like the beginning, and you have the PVT, which is the point of vertical tangency, and you have the point of vertical intersection. You have the grade of the back tangent, and you have the grade of the forward tangent. And then you have these distances, horizontal distance from the PVC, and the constants, and other offsets. Move to the next. I think the best thing to do is to direct you all to this YouTube video by the Semi Sigma fellow. Just do a search on YouTube under vertical curve example elevation. You'll see his come up. He does an excellent job of explaining the basics of these things. One thing to note, like in his first example, looking at the equation you'll be given in your exam booklet, the PVC here, he calls the BVC, he calls it the beginning of vertical curve. Just kind of watch out for that. And then the PVT, the point of vertical tangency, he calls the EVC, the end of vertical curve. That's the kind of like the big difference. Otherwise, he'll set up the problem basically using this formula, and it explains it really well. And I'll let him explain it on his video. And there's one other equation that kind of comes up, y equals ax2, that I noticed. This is like a tangent offset distance from this x. So I throw that in there. And I've got an example here I was going to do for you. This rate of change of the grade. So say using the vertical curve equations, given a vertical curve with a G1 of minus 3.2% and a G2 of positive 4.15%, a length of 200 feet, a PVI of 23 plus 00 at 600 feet. What is the rate of change for the curve? So once again, you're going to use this rate of change grade formula here. And this equation here, the way I did it this time, I went ahead and converted the percentages into decimal format and put them in the equation here. And you get an answer which is going to be per foot, a grade change of per foot. You can put it in the percent form per foot, or in a station format per station. So watch out for this formula in particular. So you can enter the G's in percents and in the L in stations. So like here's one more, the same thing. I went ahead and just used the percents as the numbers. So G2 I use 4.15. The G1 I just use minus 3.2. But the L I converted it into stations. If you do it this way, so the rate of change comes up as a percent per station. And I just went ahead and put in another example. Using the vertical curve equations, given the vertical curve of G1 is 5.1%, so it's coming up this way, and a G2 of minus 4.3, see a picture of it going down this way, the length is 450 feet. The point of vertical intersection is 14 plus 60 at 2,000 feet. What is the station elevation of the PVC? So we're going to use the PVC elevation. You're going to take the PVI elevation, 2,000 feet, and then you're going down, so you're going to subtract that grade. I left it in number format, 5.1, so I'm going to convert that 450 to stations, and this is going to be, we're going to assume that it's equal on both sides, so divided by 2. That's how you get that elevation here. And once again, I just alternatively wrote it out for you. If you're going to do these, you can do it this way too. So 2,000 minus, I went ahead and put it into decimal format, but then you're going to leave that distance as a whole number and divide by 2, and you get the same answer. And then to get the PVC station, I took the 1460, the full length, minus the 450 divided by 2 this time, and got 1235. I went ahead and put stations 12 plus 35. And once again, you're going to assume an equal vertical curve. Okay, let's go ahead and look at the next equations sets that come up in our booklet here. We have the photogrammetry equations that come up next here. I'll just go one by one and do like an example for you. Yeah, let's go ahead and do an example. We'll just use this very first equation, scale equation. So let's say we have a problem. A set of vertical aerial photographs was taken from a flying height of 2460 feet above the ground using a camera with a 6-inch focal length. What is the photo scale? So I went ahead and pulled this equation and put it right here for us to see. And so we're given f, the focal length, the small f is 6 inches. And the h is the flying height above the datum, so it's 2460 above ground. And the little h is height above datum, so we're just going to use h equals to 0 since we're just going to figure we're going to be at the ground level. Convert the height to inches, and go ahead and put it in the formula. And go ahead and simplify. So the exact scale, is 1 in 4920, and you can round it. Typically, you would say 1 in 5,000 is the scale, 1 to 5,000. Okay, let's look at another example here. A photo is taken 4,000 feet of flying height. A building is 40 feet tall. Its radial distance is 5 inches. Find the relief displacement. So here's the relief displacement equation, and I just wrote it out for us here to see. So these terms are defined below. R is the radial distance from the principal point. H is the height above datum from height of object. H is flying height above datum. So just go ahead and set up your equation, put in the terms, and you come up with 0.1 inches. So the relief displacement is 0.1 inches. Okay, the next example, for a photometric mapping project, the C factor is 1500 and the required contour interval is 2 feet. What is the required value of H? Once again, H is flying height above datum. So right there, we're going to use this third equation here. I went ahead and wrote it out for us here. So we can just go ahead and put the terms in this one. H is equal to 1500 and then times 2. You get 3,000 feet. So the required flying height above datum is 3,000 feet. And we'll do one more example with these parallax equations that you get left over here. So let's say measure parallax first. Then solve for ground position and elevation. Given all these givens, find the P, the parallax, measure the stereo pair, and then X, Y, and H, and they're defined here. So you can just put them into these equations and get these answers. It's you got to make sure you use consistent units. Photo measurements stay in inches. Ground distances are in feet. I guess just to watch out for in these equations. And let's take a look at the next set of equations that we have here. We get into the physics equations here. So what these are, this first equation is the lens equation. It's where images form between two mediums. Then you got the Snell's law, which defines like how light bends. And you got this other equation here. Distance traveled starting from zero velocity. It's how far something moves from rest under a constant acceleration. Let's take a look at this now. Okay, let's go ahead and do an example with this first equation, the lens equation. A lens has a focal length of 6 inches, and the object is 12 inches from the lens. Find the image distance. So we're going to use this very first equation. And we're given the object distance, the O, and we're given object is 12 inches from the lens, so that's the F, focal length. And so we're going to be solving for the I, the image distance. So I'll go ahead and solve for I in that equation. You get 12 inches, so the answer is 12 inches. Okay, let's do an example for the Snell's log equations here. Let's say a light ray passes from ear to glass. So and the refractive index n is equal to 1, and the second medium has a refractive index of 1.5, and the angle of incidence is 30. So you're trying to find the theta there, theta prime, this equation. So go ahead and set it up. Put all your terms in and just solve for the theta phi, inverse sine. So it comes out to be 19.5 degrees. And we'll use that other equation, that motion example equation. An object starts from rest and accelerates 4 feet per second squared for 3 seconds. How far does it travel? So we're looking at this equation here. They're trying to solve for the s, distance traveled from starting velocity 0 velocity. And go ahead and put in your terms that you know. You got the acceleration of 4 and the time of 3. Solve, and you get 18. So the distance traveled from starting from 0 velocity, s equals 18 feet. And we'll go ahead and take a look at the next set of equations that comes up here. The curvature and refraction equations. Now these equations, I just kind of put together what these are used for. These equations are used to correct for the effects of the Earth's curvature and atmospheric refraction in surveying. Curvature corrections adjust from the Earth's surface dropping away from a level line of sight. Refraction correction adjust for light bending slightly downward towards the atmosphere. Together they help improve leveling and long sight vertical angle works. This is over long distances. You might be using these. And there's one other equation, this allowable angle, angular error. It's used to estimate a small allowable angular error for one observed angle. Just do some basic examples here. This would be a basic level rod correction problem. So a level sight is 2,000 feet long. Find the combined curvature and refraction correction from the rod reading. So since we're finding the curvature and the refraction, we're going to use this I went ahead and pulled this equation right here. It's got the C and the R in there. And the D is in thousands of feet, so you just got to first convert that 2,000 feet into thousands of feet. So you divide by 1,000 to get 2, and you just go ahead and plug that right into the formula. So your CNR is just 0.0824 feet. So basically what that means is over a 2,000 foot site, the combined curvature and refraction correction is 0.082 feet. And another basic problem just using curvature only. So let's say a site distance is 3,000 feet. Find the curvature correction only from the level rod reading. So I went ahead and just pulled the other equation here for the curvature, and can once again convert the distance into thousands of feet. So I divide the 3,000 by 1,000, get 3, and then plug it right into the equation, and we're going to get 0.0216 feet. Okay, and we'll take another look at the next set of equations that we got. Oh yes, this they put in there the magnetic declination in your list of equations, and I just want to explain how to use this real quick. Basically, a true bearing is going to be equal to the magnetic bearing plus a declination. And you got to remember, if you have an east declination, you got to add it. If it's a west declination, you're going to subtract it. So a basic sample problem: a line has a magnetic bearing of north 35 degrees 20 minutes east. The magnetic declination is 6 degrees 15 minutes east. What is the true bearing of the line? And so just go ahead and write the equation that I wrote for you here, and add the east declination. Like I told you, you got to add it to the magnetic, and you get the answer is 41 degrees 35 minutes, and it'd be north 41 degrees 35 minutes east. And one more quick example. So let's say a line has a magnetic bearing of south 62 degrees 10 minutes east, and the magnetic declination is 4 degrees 30 minutes west. What is the true bearing of the line? Write the relation. And now, like I said, if you have a west declination, you got to subtract it. So you're going to put the magnetic bearing and then subtract it, and you get the answer. The true bearing is the south 67 degrees 40 minutes east. And you can do these minutes, degrees, minutes, seconds, right in your calculator. I'll give you a place where you can learn the calculators, but you can do that right in your calculator typically. The next set of equations that comes up, we'll go ahead and move right along here. Now these are the geodesy equations. And what these equations are used for, these are geodesy equations, are used to describe the shape of the Earth, the curvature of the ellipsoid, the latitude, and the relationship between GPS height, the geoid heights, and elevations. I mean, just going through these, A is the semi-major axis, it's the equator radius. The B is the semi-minor axis, it's the polar radius. You have these other equations: flattening, eccentricity, radius and meridian, radius and prime vertical. So the flattening is how much the ellipsoid is squashed. Okay. E squared, eccentricity squared, is how non-circular the ellipsoid is. This M, the radius in meridian, is the radius of curvature in the meridian north or south, and this N is the radius of curvature in the prime vertical east to west. And you have this other theta. It's the convergence in meridians that's down here, this last equation. So I'll just pick a basic example, GPS height conversion example. Let's say a point has an ellipsoid height h equals to 842.60, a geoid in relation n of 101.35, find the orthometric height. So you're going to pull this equation here. H, the small h is the ellipsoidal height, N is the geoid undulation, and H is the orthometric height. And since we're solving for orthometric height, we're going to rearrange the formula and then just put in our terms to solve. And we get an answer of 741.25 feet. Now this is the basic idea of converting a G and NS ellipsoid height to more familiar elevation above geoid, sea level, datum. That's what that's used for. And let's go ahead and do one with the flattening equation here. That's this one here. Given the ellipsoid, you have, I just went ahead and made up some numbers for the semi-major and some semi-minor axes of these. And to find the flattening, you just go ahead and put them right in the equation to get a flattening number for this one. And it's usually published as 1 over f. So, you would take 1 over that number if you wanted to get it like in a published format. And let's take a look at the very next set of equations that comes up now. It's the measurement of areas and volumes. So you have these different circular segments, circular sector, and sphere. Very briefly, I just went ahead and defined out the terms. A is area. They give you these here. P is perimeter, V is volume, R is radius. You can see there. D is segment height. It's right there. S is arc length. It's over like that. And the phi is central angle in radians. Now for circular segment and circular sector, these formulas, the sheets are in radians. That's important to kind of watch out for. So if your calculator is in degrees, you're going to need to switch it over to radians mode to get these equations to work for you, unless you convert radians to degrees, in the formulas. But I would just get in the habit, if you're doing one of these problems, switch your calculator over to the radians, and then for most of the stuff you're going to use degrees. But maybe give me an example here. So let's say, let's go ahead and use this circular segment example. Circular segment has radius of 10 feet, segment height of 2 feet. Find the segment area. Step 1, find the angle. And we'll just use that equation down here. And we have all the terms, the radius, the segment height. So we get that. And to do this calculation or calculator, you got to have it in radians once again, the way it's set up. And then the area, you're going to use this other equation, put in the terms, and make sure it's in radians again. You get 16.35 feet. And that's the area right above that here, we just calculated. And let's do a circular sector problem. Let's say the sector has a radius of 12 feet, arc length of 9 feet. Find the sector area, which is the whole kind of like pi area. Find the angle. So we're going to pull that equation, that second one down there, and put our terms in and get 0.75 radians, and find the area with the other one. Put our terms in, you get areas 54 square feet. And let's go ahead and do a sphere example problem here. A sphere has a radius of 3 feet. Find the volume and surface area. So we have these two equations here. Let's do the volume. That's that first one I just set up here for us. We're given the radius, so you can go ahead and put right in that formula, and you get a volume of 113.11 cubic feet. The surface area is that next equation there. I went and put it here. And you go ahead and put the radius in again, and this one comes up in 113.1 square feet. So you have volume in cubic feet, area in square feet, this one. And I just put that again, make sure for circular and circular segment, use the formulas exactly as shown on the sheet. You got to make sure you're in the radians mode. But for most ordinary surveying trigonometry problems like angles, bearings, triangles, working angles, you're going to make sure your calculator's in degrees mode. You got to watch out for that. And let's look at the next set of equations that come up in our booklet here. The next set of equations are these state plane coordinates. These state plane coordinate equations are used to convert measured ground distance into a grid distance on a state plane map projection. And they do a pretty good job of giving you the equations and what the terms are here. You have this other arc distance. Let's go ahead and just do an example. So let's say a line has a DH, which is a horizontal ground distance, 1,000 feet, and H, which is orthometric height, 500 feet, N, geode height, and an R, ellipsoid radius, and an SF, which is a projection scale factor. Find the ellipsoidal distance and the grid distance. So we can use this equation here for the elevation factor. Put in your terms. And step 2, reduce the ground distance to ellipsoid distance using this formula here. Solve for dE. And then you can reduce the ellipsoidal distance to a grid distance. Solve for the dG with this equation. And you get these answers here. Okay, let's look at this last equation. Arc distance to chord distance correction, where R is in the radius of the arc distance. So let's do an example. We have the CH correction, 10,000 feet, and the R, the radius, 20,906,000 feet. So we're trying to get this this whole correction. Go ahead and set up the equation like that. You got the CH, put that there and cube it. 24 feet times the radius squared, and then you get that term 0.000095 feet. So what that means is arc is only about that much feet longer than the chord for that line. And let's go back to our reference book now and go to the next equations that come up. And you get this electronic distance measurement formulas that come up here. You know, it's velocity of light through the atmosphere, the velocity of light, vacuum, index of refraction, wavelength, modulated frequency, distance measured, integer number of wavelengths, fractional part of wavelength. You have this correction. We'll go over that next, but just do a basic example. You have a EDM, electronic distance measurement instrument, has these numbers. So let's say we're given the C, the N, the F, the M, the D, find the distance. So first, find the velocity, put your terms in, calculate velocity, and then use that. That's the next one for the wavelength, put your terms in, and then thirdly, you can use the distance formula there, set it up. And I put our terms in that we calculated, and that one I did in meters, so it's 2003.4 meters. And the reason I did it in meters is because these formulas all are in meters. And going back to the last atmospheric correction. So it says, 10-degree temperature change or pressure difference of 1 inch mercury produces a distance correction of approximately 10 parts per million. Here's a quick example. So let's say you have a line measured as 1,000 meters. The temperature pressure causes a correction of 10,000 ppm, let's say. So ppm, you basically set that equal to, that's 10 over a million. It's like a ratio. So in your correction, you just multiply it by your measurement, and it's 0.01 meters, so that's your correction for that distance measured in this case. And let's go ahead and move right along to the next set of equations in the book here. You have these area formulas, area by coordinates, trapezoidal rule, and Simpson's 1/3 rule. Now this equation, I've had this in classes and before, but this guy here does a great example of how to do it a lot easier. So I want you guys to go look on YouTube for this. You can just type in, I put the link here, but you can just search on YouTube CE 452 Lecture 7 FE Exam Review Land Surveying 2020, October 7th. So just search on that and this will come up, and it's example number 3. And then for these other two equations, once again, somebody else has a good video already on this on YouTube for the trapezoidal rule and Simpson's rule. Just search on this YouTube video. It's called FE Made Easy Trapezoidal Rule. I like these guys. They did a good, you can see it's like 10 minutes, and they show you a real good example how to use this formula. So I won't get into that on this. Let's go ahead and take a look at what comes up next in our equation book here. And these are our earthwork formulas that come up. You have average end formula, volume, prismoidal formula, and the pyramid or cone comes up. And I was going to tell you for this volume formula, I like that same guy. Just look at example number 4 in YouTube, search on his video. And for the prismoidal, I like this Mark Madsen guy a lot. Just search on Mark Madsen FE Civil Review Surveying Review, and it's number question 7, and it'll kind of start out looking like this. He does a great job on the prismoidal formula, how to do that quickly and easily. So I'm going to go ahead and do an example for the pyramid or cone right here. Do a pyramid example. So let's say you have a pyramid shaped stockpile, square base, 20 by 20 feet, height at 12 feet, find the volume. So we're going to use this equation. I went ahead and put it here for us. Well, and it's right here, sorry. And see, the first thing I do is calculate the base area, 20 by 20, so that's 400 square feet. And they're going to put that into this equation here, and you have the h height given. So you get a volume for that pyramid stockpile of 1,600 cubic feet. And we'll do a cone example. Let's say that you have a cone stockpile, and the radius is 6 feet, height of 15 feet, find the volume. So go ahead and calculate the base area. So the area of a circle is pi r squared, given the radius, so you get 36 pi. Now use the formula, and the area goes in there, height goes in there, and you get 565.49 cubic feet for the cone stockpile. And moving right along, let's look at the next set of equations that we have here. Now you get into the probability and statistics. You have these formulas here. Start out with the standard deviation. I wouldn't really get into the nuts and bolts too much on these. I was going to reference you to this good YouTube video, how to use your calculator. I like to use the TI-36 Pro calculator for the exam. Now if you search on this YouTube video, it's called TI-36X Pro Mean Standard. Oh, hold on a second. This one's just on the standard deviation. And the other one, the general one, how to use the calculator overview, is this TI-36X Pro Review and Feature Overview. And performing a standard deviation on there is just a snap. You can do it real quick. And you have these error propagation formulas. So we'll go ahead and just go through these examples. The first one is this error of a sum that comes up here is this first one. So it's used for the total uncertainty of n repeated independent measurements in a series, okay? So let's say you have a distance that's commuted from two independent parts with standard deviations. So you have these two standard deviations, and then find the standard deviation, the total. So for this one, we're going to use the sum formula there, and you just put your different standard deviations in there and you calculate out that answer. Error of a series is the next one. That's used for the total uncertainty of n repeated measurements in a series. So let's say you have a tape measurement with a standard deviation 0.02 feet. It's repeated 9 times in a series. Find the series standard deviation. So on that equation I wrote it out here for you. And you just put your standard deviation in there, and you have 9 measurements, n is 9, so you get 0.06 feet for that error. And then you have error of mean problem, so it's this formula here. It's used to find the precision of an average of repeated observations. So let's say you have the same observation, standard deviation of 0.02 feet, and it's observed 9 times, find the standard deviation of the mean. So this one, you set up this formula right there, and you put in your standard deviation and n. So this gives you the standard deviation of the mean, error of the mean there. Yeah, the next formula that comes up is the error deviation product. So we're going to use this one. So a product is like something multiplied by each other. So like area is, side A times side B, so it's equal to A times B. So use this formula since area is calculated by a product. Okay. So for example, say A is 100 feet one side, and the other side has 50 feet width. Now these are standard deviations of these measurements of each of these sides. Okay. So you're going to use this, find the standard deviation of the area, use this product formula here. I just go ahead and put it over here, and you put your terms in. A is equal to 100, B is equal to 50. And you have the standard deviations for each, and you put those in accordingly. And then you calculate that out, and you get an answer of 2.5 feet squared. Error of product problem. Okay, this next one that's here, it's this covariance matrix you can set up. And I got an example problem. So let's say a point has a standard deviation for the x of 0.05 feet, for y 0.08 feet, and for xy 0.0012 square feet. Write the covariance matrix. So you're going to square the standard deviations and just set it up just like it is in this formula here. And you put all the numbers in, and it's like in a matrix form. You can solve the matrix on your calculator if you want to, but that's the basics for that one. And this last formula is like an error ellipse orientation problem. So it's like used to find the rotation angle of the error ellipse from the x-axis. It's this formula here. I'll give you an example. So you have these terms once again, and find the error ellipse orientation angle. So I'll go ahead and write the formula out for us here, and you put in the terms, solve for theta, and it comes out to be negative 15.8 degrees. And coming back to our reference handbook, let's see what we have next. We have the relative weights and the weighted mean. Okay, so let's do a basic problem. For the relative weights, it's basically so the most precise observation gets trusted the most. Okay, so say for instance a distance was observed 3 times. First measurement is 100.12, standard deviation of 0.02 feet. M2, second time it comes up measured as 100.08 feet, the standard deviation of 0.04 feet. And the third measurement comes up to be 100.1 feet with a standard deviation of 0.01 feet.
find the relative weights and the weighted mean. So for the relative weights, we're going to use this formula here. And you go ahead and set it up. And you're going to use these, you're going to do one for each one. So if like for the first one, you put in standard deviation, and for the second one, you square the deviation, and for the third measurement, you put it in. So the relative weights are 2,500 to 625 to 10,000. And if you divide by 625, so it's 4 to 1 to 16. And then finally, we're going to compute the weighted mean. So you're going to multiply each measurement by its weight and then add those up and divide by the sum of the weights. So like this formula here is this one here. The weighted mean is the sum of the individual weights times their measurements divided by the sum of the weights. So from the previous slide, we put in these numbers here and the measurements, and then back at the weighted means here. So then, so the weighted mean is 100.10 feet. And let's go ahead and see what equations we have coming up next here. We have these confidence intervals, and it's the statistics here. So we have these basic problems. I'm going to go ahead and do one mean confidence interval where the standard deviation is known problem. So I'll stick with this first equation here. So let's say we have a distance is repeatedly measured. Sample mean is x equals to 100 feet. The known population standard deviation is 0.2 feet. Sample size is 25. Find the 95% confidence interval for the true mean. And so I'm going to write down the formula right here. You can see this one's got that z value, and this is the value of the z's here. So for the 95% confidence, you pull out that 1.96 for that factor there, and you go ahead and put the numbers into the 12th equation, and it's formed interval. So it's this interval that you get, the confidence interval. It's between these two. And a confidence interval for a variance problem. So I'm going to do one on this one here. A sample of n equals 16 observations as a sample variance x squared, 0.04 square feet. Find the 95% confidence interval for the population. So in this case, for this formula to work, I'm going to have to assume that we have some of these values from this formula. And I'm going to go ahead and put them in the equation here and substitute them out. So then the lower limit there, we have this number here from that we assumed upper limit. So it's between these two numbers. And let's go ahead and look at the next equation set that we have now. Three-wire leveling. I think the best example that Mark Madsen guy does a nice job. If you see his FE Silver Review, Surveying Review, see question 13, he does a good job of they kind of run through that basic, how to do these. I'll let you guys go to him to get that. And let's go to the next equations that come up here. These are these matrices that come up. So you have all the multiplication, addition, inverse, the properties and determinants. I was going to tell you to go watch this TI-36X Pro review overview of the calculator, just search on that in YouTube. And you can do a lot of these calculations for the matrices right on your calculator a lot easier. So I'm going to send you there to learn that. Okay, let's go ahead and go to the next set of equations in our reference book. Okay, you come up to these conic sections. So like this first part here, E is equal to eccentricity equals cosine theta over cosine phi. It's shown at these sections of this here. Note x and y in the following cases are translated axes. So like eccentricity, E tells you what type the conic curve is. So basic formula I just wrote out for us here again. This tells the type of the conic, so if E is less than 1, it's an ellipse. It's equal to 1, it's a hyperbola. When it's a parabola, and if it's greater than 1, it's the hyperbola. Okay, let's go ahead and look at case 1, the parabola. That's where the E is equal to 1. Okay, so basic sample problem. Let's say we're given a parabola, y squared is equal to 8x. We want to find the vertex, focus, and directex. They give you this in the equation book. It's a standard form of the equation. So I wrote out the equation here and then compared to this equation. Now the center, I went ahead and set it just like they say, h equals to k equals 0. So the standard form here is the y squared 2px. And in this case, the 2p is equal to x. That's the part in front of it. So you solve for the p and get 4. Now find the vertex. Since there's no shift we're consuming, it's just going to be 0 like we said. The focus, see how they say p over 2 comma 0. So use the p over 2 comma 0. So 4 over 2, since we calculated that p over there, so it's 2 comma 0. And find the directex. It's x equals minus p over 2. So just calculate that out. Put 4 in for p, so you get minus 2. So that's your answers there. That's basically how to do this one here. Okay, then we get to the case 2 example that's in that form of the book, where the ellipse E is equal to less than 1. So let's go ahead and jump to an example given this ellipse. X squared over 25 plus y squared plus over 9 equals 1. Fine, we're going to find the center A and B and eccentricity. So the standard form of the equation they give you right here, just go ahead and write that out. In this case, like we say, the center, we're just going to have it 0, 0. So, a squared, this term here is that a squared equal to 25, so a is 5. B squared is 9, so it just b is equal to 3. So eccentricity, we're going to use this formula here. He's going to put your a's and b's in there, calculate at 0.8. And we have case 3, hyperbola, where e is greater than 1. Let's say, given this example problem, given the hyperbola, find the center A and B in eccentricity. Read the standard form, compare it to the standard form they give you. Once again, use h and k as 0 as the center. And our a squared in this case is equal to 16, and b squared is equal to 9. So you get a is equal to 4, b is equal to 3. Find eccentricity with this formula there. And you go ahead and put your terms in. You get e is equal to 1.25. And case 4, where you have a circle where e is equal to 0. Okay, so very brief breakdown. A circle equation is this right here. That's the circle equation where the center is hk, and you have a radius that you can calculate. That's this here. So it's used to tell you when you know the center and point on the circle, and then you get the tangent length from outside a point with this equation here. It's used to find the length of the tangent from outside a point on the circle. And let's do a sample problem for those equations. So a circle example. Let's say a circle has a center of 3, 4, radius 5, right out the equation in the standard form. here's a standard form. Substitute out the numbers, and you go ahead and write it out, and it's basically just the answer for the equation of circles. And then to get the radius from a point, so let's find the radius of a circle with a center 2, 1 passing through the point 6, 4. So you use x and y as your point, and your center is going to be your 2, 1 that you put in for the h and the k. So then you get out that the radius equals out to 5. That's how you do this second formula. And an example for the tangent length, let's say the circle has a center 0, 0, radius 5. Find the tangent length from the point outside at 13, 0. And I wrote out that standard formula that we're given, I substitute in the values x prime, x, y. That's that point outside here. And the center, we had h and k, so we put in zeros for there. We know the radius given is 5, we put that there. Calculate it, solve for t, and you get t is equal to 12. Okay, let's take a look at the next set of equations that we're given here now. Okay, we get these conic section equations. So I just went ahead and kind of run down what these are. You get that general conic equation. This can represent a ellipse, hyperbola, parabola, circle, or even a straight line. So you can see they have these classification tests. You're going to use like the b squared minus 4ac. And if depending on what it falls into, you either get an ellipse, hyperbola, parabola, or a circle. So then we can do an example now. Let's do some basic problems, classify this conic problem. Classify the conic. Here's an example. I wrote out a sample. So the first thing you do is identify the A, B, and the C. So A is a 3, and got 2 for B, and the C here is the 2. Compute the discriminant b squared minus 4ac minus 20. And then since that minus 20 is less than 0, this conic is an ellipse. And then another one, find the center and radius of a circle problem. Write an equation, find the center and radius. Okay, match to the circle form. So then you can see A is equal to, the 2A is equal to minus 6 right there. So A is minus 3. That 2B form is equal to 8, so B is equal to 4. And then that C is equal to minus 11. So if the center is that A is equal to 3, and the B is the minus B, so this one's 4. So the center is 3 minus 4. Then find the radius using that formula. Put in your A's and the B's and the C's and calculate out the 6. And just basic stuff for that. Okay, let's go ahead and see what next equations we have in our booklet here. Okay, we come up to differential calculus. You got derivatives, partial derivatives. I say in plain English, the first derivative is the slope, it's the rate of change. Second derivative tells whether the curve bends up or down. The partial derivative is the rate of change with respect to one variable only. And instead of getting into the nuts and bolts of this too much, once again, I'm going to send you to this good YouTube video on the TX30X Pro review, and you could actually do derivatives on your calculator. So don't spend too much time on this stuff here. So I went ahead and put a basic problem here, a derivative, a slope example problem. So given this equation, find the derivative and the slope at x equals 2. So differentiate this here, so you bring the 2 down, you get 2x, and 3, you drop the x, that comes out to 0, so that's the first derivative, and substitute into the x into that equation, so 7. So The first derivative is that number, this equation there, and the slope at 2 is equal to 7. And the maximum minimum problem, since they kind of get into this here, determine whether the function has a minimum or maximum. So we're going to go write out the first derivative again, set it equal to 0, and x is equal to 2. I'll find the second derivative of that, so it's just 2. And since the second derivative 2 is greater than the 0, the function has a minimum at x equals 2. Okay, let's do an example point of inflection example. So since they do test for a point of inflection here. So let's say find the point of inflection of this equation here. So find the derivatives, either the first derivative, it's 3x squared, second derivative is just 6x. Set the second derivative equal to 0, like they say here. So x is equal to 0. Check sign change for x greater, x less than 0 if second derivative is less than 0, and then for x greater than 0 if second derivative is greater than 0. So the sign changes at x equals 0 in this case. Find the point. So the answer is 0, 0 with this example. And they have this partial derivative mentioned here, so we'll do an example. Let's say you're given this equation here. Find the partial derivative of x with respect to x. So you're going to treat y as a constant in this case, and take the partial derivative of x. So it's 2xy, and then partial derivative expect that again is 4y squared, this part here. And then combine the terms, this one plus this one, so the answer is basically that. And let's go ahead and look at the next set of equations that we have in our booklet now. So what you get now is these unit normal distribution tables that comes up. I'm just going to read this what this table is used for. This is unit normal distribution table. It's used to find probabilities. Standard normal variable z, where basically z is x minus u over sigma. So I guess for a survey reviewer class, it's useful for probability measurements, error beginning with limits, confidence intervals, testing whether an observation is unusually large or small, converting a measured value to a z-score. In plain English, it tells you how much area is under the normal curve left, right, between the z values. Okay. Very brief breakdown of the columns. These are the x, z values. Okay, and the function of x is the height of the normal curve at that z. Fx is to the left of the z, and Rx is to the right. 2xr. This one here is the two-tailed outside plus or minus z, and this Wx is the area between the minus x and z. So common confidence intervals, are these z values. I'm not going to get into this too much more than that. Let's do a basic sample problem. Probability to the left problem. So find the probability that a standard normal variable is less than 1.2. So go to z is equal to 1.2 right here. And we're looking for the probabilities to the left. So we're going to go over to 1.2, and here's our number, the 0.8849. So we pull that from the table. and that's your answer. So there's 88.49% area to the left of Z at 1.2, and then probability to the right problem. Find the probability that a standard normal variable is greater than 1.2. So use the right tail column now. So we're going to use this this right tail one here. So R equals 1.2. It's 0.1151. So we're going to pull this value right here from the right side. And it's greater than 1.2 is 0.1151. So there's a 11.51% area to the right of the C value of 1.2. Okay, let's go ahead and look at the next set of equations. This comes up in our booklet now. Okay, we get the T distribution table. You're going to use the T table for confidence intervals on a mean when the population standard deviation is unknown, especially with small samples. Okay. And the main formula is this, if you go back to that confidence intervals, where X is the sample mean, and this is a value from the table, this sample standard deviation, number of observations, and degrees of freedom. And the table meaning the left column is degrees of freedom, top row is the tail area, and the table value is a critical T value, okay? Basic sample problem. Let's say a survey crew measures 10 times and gets a sample mean 250 feet. The standard deviation is 0.3 feet. Find the 95% confidence interval for the true mean. Find the degrees of freedom. You just take the sample size and -1. That's the degrees of freedom. You get 9. Pick a T value. So for 95% confidence interval, use X over alpha over 2 is equal to 0.25, okay? And from the table at 9 degrees freedom, you get this T value of 2.262. You compute your standard error, compute the margin of error, and then form the confidence interval, so you get the confidence interval between those. Let's look at the next set of equations on our booklet now. Now this next one is this F distribution table. This F distribution table is used to compare two variances. For a surveyor, it's useful for checking whether two data sets have the same precision. Comparing the variance of two crews, for example, two instruments through two methods, variance ratio test in plain English, is one set of measurements significantly more variable than the other, okay? A very brief breakdown, the F statistic is this setup here, first and second sample variance. It's usually put the larger variance on top, so it's greater than 1. And you get your degrees of freedom, so you get like a decision rule. If it's computed greater than F table, variances are significantly different. If it's computed F is less than the table F, the variances are not significantly different. We can do a basic sample problem. Two crews measure the same type of line. Crew 1 has 11 measurements, variance squared of 0.04. Crew 2 has N2 of 16, variance squared of 0.01. At the 5% level, test whether the variances are significantly different. So you put the larger variance on the top, you get 4. Find the degrees of freedom you're going to subtract out from the sample sizes. You can look up in the table for the degrees of freedom of 10 and 15, and you're going to get a value, and then you can compare it to the computed value, since 4 is greater than that number that you looked up, the variances are significantly different at the 5% level, so you reject the equal variances is how that works. And let's go ahead and look at the next set of equations in our book now. Okay, the next stuff that comes up is the economics. You have, future given present and everything else. It defines it pretty good here. And you have some depreciation straight line and accelerated depreciation book values and benefit cost analysis. For engineering economics stuff, I'm going to refer you back to Mark Madsen. Just look up his, go on your YouTube, search in FE Ethics and Economics session. And you start the economics section. He does a good job of that. And also the other guy, the CE 452 one, search on this here and look for example 3 and to give you a good kind of basic example how to use these tables here. And that's all I have. Thank you very much. That's just a quick rundown of all the equations. And remember, on this test, they're not going to give you too long of a problem because I think you only have, 3 minutes per problem. So you have to think that just knowing the basics of these problems, so don't get over concerned on them, just kind of know the basics like this. Okay, thank you.